Written into these rocks is a fundamental truth about the universe. A truth that we can find written throughout the natural world.
One of the wonders of the natural world. It's beautiful.
The bee's honeycomb is a marvel of natural engineering.
They've got plenty of honey.
Everything they need is here. It's a place to raise their young and store their food. And it's all made from wax, a substance so labour-intensive that the bees have to fly the equivalent of 12 times round the Earth to produce a single pound of it.
This almost looks man-made, manufactured. I mean, it doesn't look like something from the natural world. The precision, the fine straight lines that they've created is extraordinary.
Right. It's an engineering wonder for sure.
Look at that, it's perfect. Hexagons here.
It is amazing. And the hexagon is a very strong structure.
The bees have made an identical pattern to the columns on the Giant's Causeway. Each cell is exactly like the others, 6 walls meeting precisely at 120 degrees. And every honeybee, everywhere in the world, knows how to build these shapes. It's as if the hexagon is built into the bee's DNA.
You can see the bees going down inside the cell. It's almost exactly the same size as their bodies. So are they using their body like a ruler in some sense to do the geometry?
I would say that's an accurate description. I know different races have a smaller body and the cell size in their comb is smaller.
And each of the hexagons, how do they actually make a hexagon rather than some irregular shape?
They've just done it for thousands and thousands of years. They were born to do it. They just instinctively know that this is the shape of their home.
But there's more to the bee's behaviour than raw instinct. There's another reason why they build in hexagons. And to reveal that reason, we need to turn to the universal language of all nature, mathematics. The bee's primary need is to store as much honey as they can, while using as little precious wax as possible.
The bee's honeycomb is an amazing piece of engineering, but why have they evolved to produce this hexagonal pattern? Well, actually, they don't have too many choices. If you try to put pentagons together, for example, they just don't fit together nicely, or circles leave lots of little gaps. If they want to produce a network of regular shapes which fit together neatly, then you've really only got 3 options. You can do equilateral triangles, or you could do squares, or you can do the bee's hexagons. But why of those 3 does the bee choose the hexagons? Well, it turns out that the triangles actually use much more wax than any of the other shapes. Squares are a little better, but it's the hexagons which use the least amount of wax.
It's a solution that was only mathematically proven a few years ago. The hexagonal array is the most efficient storage solution the bees could have chosen. Yet with a little help from evolution, they worked it out for themselves millions of years ago.
This is nature's code at work, and the bees are in tune with it.
It's easy to see why efficiency is important to the bees. After all, it's hard work making wax. But what could be the reason for the same pattern being permanently engraved in the rock of the Giant's Causeway? The geological processes that form these columns took place over thousands of years. But to understand what happened, we need to look at structures that last for only a few seconds.
are different thicknesses of soap film. So looking over the colors of a bubble, you're actually looking at a contour map of the surface of the bubble. So like everything in nature, bubbles are just trying to economize. They're trying to get as small as they possibly can. But in the case of bubbles, they can do it perfectly. A single bubble in the air is always a sphere.
At first sight, it seems obvious that the bubble should be round. But why is the sphere so special? The sphere is one surface, no corners, infinitely symmetrical. Of all the shapes this bubble could be, the sphere is the one with the smallest surface area, which makes it the most efficient shape possible. And it is because nature loves to use her resources effectively that we can see spheres everywhere we look. The Earth is round because gravity pulls the planet's bulk into a ball around its core. Water forms into spherical droplets. The shape minimizes the amount of surface tension needed to hold the droplet together. And a spherical shape gives simple life forms, like this volvox plankton, optimal contact with their surrounding environment. But not everything is spherical. And because bubbles are so thin and flexible, we can use them to create other shapes.
So a single bubble in the air is always a sphere. But if they touch each other, they can save material for both of them by sharing a common wall. And so they do. If they can save surface area by taking advantage of their environment, they will.
So when you've got just one bubble, the sphere is the most efficient shape. But as we add more bubbles, we see the geometry changing. So in this case, we've got 4 bubbles, and you can see them meeting at a point. But put a shape in the middle, we don't get a spherical bubble. We get, in fact, a little tetrahedron. With 4 faces, they're not exactly flat, they're parts of spheres. But each time, the bubbles are trying to find the most efficient shape for the arrangement of bubbles. So now we've got 6 bubbles, we've got a little cube appearing in the middle. This is nature's laws at work. The universe is always trying to find the most efficient solution it can. And as we pop them, bubbles change, finding the most efficient, until we're left with a sphere again.
It has no choice.
But what's most remarkable is that those solutions are so often neat geometric shapes. Wow, that's a dodecahedron. That's fantastic. And they're almost perfect pentagons, aren't they? That's really surprising. They're not bulging really very much at all.
That's right.
So 12 bubbles around make 12 faces, and the most economical shape that they can make, the lowest energy, is the dodecahedron.
Yeah.
The soap bubble reveals something fundamental about nature. It's lazy. It tries to find the most efficient shape, the one using the least energy, the least amount of space. And it appears there are fixed rules about how it finds these economic solutions. The bubbles are incredibly dynamic, but each time one pops, they're always trying to assume the most efficient shape, the one that uses the least energy. And what they're doing is trying to minimize the surface area across the whole bubble structure. This beautifully illustrates one of the fundamental rules of bubbles, which is 3 walls of a bubble will meet always at a 120-degree angle. Wherever you are in the foam, it's the same law.
But if we in fact make each of the bubbles the same size, a rather magical shape starts to appear. The hexagon.
And when you pack lots of hexagons together, the pattern that spontaneously emerges is the familiar sight of a tightly ordered honeycomb.
So when we see that pattern at the heart of the beehive, it is in fact echoing some of the fundamental geometric rules of the universe.
It's the principles we see in bubbles that help explain where all structure comes from. And it's those same fundamental laws of shape that played out on the Giant's Causeway in the distant geological past.
50 million years ago, before there was any thought of warring giants, this area was very unstable. There was a huge amount of volcanic activity. The molten rock forced its way through the chalk beds beneath my feet, and then spread out, forming a huge lava lake.
As it cooled, the lake contracted, and as it shrunk, it cracked. And as the cracks spread, they sought out the most efficient path through the lava, which turned out to be this neat hexagonal pattern, leaving this monument to the order and economy of nature. We find it in other cultures all over the world. The Egyptians had their pyramids, of course, but it was the Greeks who first took this innate fascination with shape and turned it into a subject of its own. They believed that by understanding its principles, they could describe the whole world. And they gave a name to this new idea, one which meant measuring the earth. They called it geometry.
The mainstay of Greek geometry was the discovery of 5 perfect shapes now called the Platonic Solids, after the Greek philosopher Plato, who believed these were the building blocks of nature. So we've got the tetrahedron with its 4 faces, the cube with its 6 faces, the octahedron with its 8 faces, the dodecahedron 12 faces, and the most complicated shape of all, the icosahedron with its 20 faces. Today, these are more commonly known as dice.
We're all used to the familiar 6-sided dice. But these 4 other shapes have also been used as dice for centuries. What makes them perfect for the job is that they are so regular. The faces of each are all the same shape, all meet at the same angles. It means that there's no way of telling one end from another, and that they are equally likely to land on any face. But most surprisingly, these are the only 5 shapes like this that can possibly exist. They're the only perfectly symmetrical solids.
It's this almost magical symmetry which made the Greeks believe that these shapes were so important. They associated them with the building blocks of nature: air, fire, earth, the cosmos, and water. These 5 shapes built the natural world. It's very easy to dismiss this approach as naive. After all, it's clear that the world around us isn't made out of just 5 neat geometric shapes. But perhaps we should have more faith in this ancient intuition. Because by laying out the laws of geometry, the Greeks had in fact tapped straight into the code that shapes all nature.
That's stunning, my God. I've never seen anything like this. In fact, I think this is the only one like this in the world. It's absolutely amazing. It just goes on and on down through the cave.
The cave is full of perfectly cubic crystals that mirror the geometric precision of the Platonic solids.
These cubes are amazing. I mean, look at that. The surface there is perfectly flat, and if you run your finger down the edge here, it's so sharp, comes down to this precise right angle. I mean, an architect would be happy with that kind of precision.
Isn't it real?
Even if you look inside, you can see just all the cracks are right angles and geometric shapes. Totally surreal. Actually, this isn't anything particularly special. This is just sodium chloride, which we know as salt. This is what you stick on your chips. But, I mean, you don't generally see salt as big a cube as this one here.
How these crystals were able to form with such perfect precision was a mystery until just over 100 years ago, when X-rays were discovered.
The geometric shapes which we find at the heart of our cells are the most efficient that nature can produce. It seems like the Greeks could have been right after all. It's their shapes that build the world around us and produce its inherent beauty.
The code dictates some shapes through efficiency, and others by providing frameworks for the tiniest particles there are.
This is nature's code.
What the Greeks discovered in mathematical theory is to be found at the heart of nature, from crystals to viruses. It all seems very neat.
I recognise that. That's an iPod. I think this is the only one like this.
But our world isn't filled with precise geometric shapes. It seems random, disordered. To find out why, we need to look to the sky and the crystals that fall from it. Snowflakes assemble themselves in the heart of frozen clouds and fall to Earth in a dazzling display. And if there's one thing we know about snowflakes, it's that they're all perfectly symmetrical.
Think of the snowflake as something which is beautifully symmetrical, but actually that's just some idealized notion. And the reality is that they're actually much more complex and irregular than we think they are.
At the molecular scale, it's quite perfect, but as the crystal gets bigger,
Yeah.
the atoms don't hook on always exactly the right way. So when it grows, how it grows depends on the environment, the temperature and the humidity. So it starts growing one way, and then it moves to a different spot in the cloud and grows a different way, and then a different way and a different way. And so by the time the crystal hits the ground, it's had a very complex growth history, and so it ends up as a very complex crystal. Oh, there it goes.
It seems that you can only come so far in trying to describe the world with simple geometry. You can see it at work in the salt crystals in the crystal cave, but in truth, that's one of the very few places in the world where you'll find such crystals. The bees use simple geometry to make their honeycomb, but they've evolved to perform that task over many thousands of years. And it's only occasionally that you'll ever find a purely symmetrical snowflake.
Because although everything is formed from tidy geometry at the atomic level, that underlying order falls apart amid all the competing forces of our chaotic world. Even the Giant's Causeway isn't really a neat hexagonal array.
It's almost there, but amongst the hexagons, there are pentagons, seven-sided columns, even a few with 8 sides. That network of perfectly interlocking hexagons just doesn't exist.
The world clearly isn't just built from simple geometric shapes. The movement of the sea and the flow of the waves are far too complicated to explain in these terms. It's difficult to imagine how we could ever find a code to explain all this complexity.
But what if there are patterns, the chaos of nature? Patterns that we're not aware of, but that we're attuned to on a subconscious level?
Fractals are how nature builds the world. Clouds are fractal because they display the same quality. Giant clouds are identical to tiny ones. And it's the same with rocks. From appearances, you can't tell if you're looking at an enormous mountain or a humble boulder. And then there are living fractals, like this tree.
It's quite easy to see how fractal it is, because if you take one of the branches, it looks remarkably like a small version of the tree itself. And if you look at the twigs coming off the branch, they have the same shape. So you see the same pattern appearing again and again at smaller and smaller scales.
And trees also demonstrate the great powers of fractal systems. Their great complexity stems from very simple rules.
Now, the reason the tree makes this shape is because it wants to maximize the amount of sunlight it gets. Very clever, but also very simple, because you just need one rule to create this shape. What the tree does is to grow, then divide, grow, then divide. And by using this one rule, we get this incredibly complex shape we call a tree.
This is the same pattern repeating itself at a smaller and smaller scale. It's a rule that's easy to test. Grow a bit, then branch. Grow a bit, then branch. And before our eyes, a mathematically perfect tree appears. But just as you never get a perfect snowflake, you never get a perfect tree either. But allow for some natural variability, different growing seasons, the wind, an occasional accident, and the result is a very real-looking tree. And we find the same fractal branching system time and again throughout nature. This idea that the patterns of nature may be inherently fractal was pioneered in the 1970s by French mathematician Benoit Mandelbrot. This is his most famous creation, the Mandelbrot set. Its systems of circles and swirls repeats itself at smaller and smaller scales forever. And this infinite complexity was created from just one very simple mathematical function.
But that code is a complicated one. If we want to understand the shape of the world, then we need to recognize the simple geometry of form at work at the most basic level.
We need to understand that the universe is lazy, and that it will always seek out the most efficient solution. That at the atomic level, the world is structured around strict geometric laws that were first recognized by the Greeks thousands of years ago.
We also need to appreciate the complexity of that geometry, playing out against the competing forces of the natural world.
And that means grasping how even the apparent randomness we see around us is underwritten by mathematical rules like fractals. Rules that can explain the patterns in everything, from the chaos of Jackson Pollock's paintings to the structure of trees and the realism of virtual worlds.
And that's the beauty of the code. However complex we find our world, it provides a reason, an underlying explanation for why things look and behave as they do.
This is nature's code.